In this lecture, we're going to talk about Rolle's theorem, which is the first step on the way to the mean value theorem. The statement of Rolle's theorem is that if f is a continuous function on a closed interval from a to b, and differentiable on an open interval from a to b, and finally if f of a and f of b are equal, then there must be an x value c in between a and b such that f prime of c is 0. Well, let me give at least a brief idea of why this is the case. So we have an interval here from a to b, and if we're supposing that f of a equals f of b, so that means there's some height, where if I plug a and b into f, they both give me points at that same height. And so roughly speaking, the idea is that either the function is going to be a constant function, so that it just goes all the way across from a to b. And if that's the case, then in fact the derivative is 0 at all of those points. But if it's not constant on that range, then it will either have some point that is higher or some point that is lower. And if there's some point that is higher, well, what happens is that if you look for the absolute maximum of f on this interval, if I have some point in the middle that is higher than the two endpoints, then that absolute maximum doesn't happen at the endpoint, and so it must happen at a local maximum in the middle somewhere. And finally, that local maximum, what we know is that the local maxes of continuous functions either look like rounded peaks or sharp peaks. But at a sharp peak, remember that the derivative is undefined. And since we are assuming that f is differentiable on this interval, which is just a fancy way of saying that f prime exists on this interval, well, that means that we can rule out the sharp peak, that there must be a rounded peak at which you have f prime equal to 0. So roughly speaking, that's why Rolle's theorem is true. Now, how can we use Rolle's theorem? Well, here's a common type of example. What we're going to do is we're going to prove that the function f of x equals x cubed plus 2x minus 1 has at most one root. In other words, that it crosses the x-axis at most once. So how do we do that? Well, first of all, notice that since f is a polynomial, that means that it is continuous and differentiable everywhere. Right? It's important to check this, because if a function f is not continuous or not differentiable, then Rolle's theorem might not apply. Right? You can't use it if you don't satisfy these sort of preconditions. So in this case, I can use Rolle's theorem. So let's just suppose for a second that there were 2 roots. Or maybe 3 or 4 or 10. But if there are 10 roots, then there are some 2 roots. And what we mean by a root is just that there are values, say, a and b, such that f of a equals f of b equals 0. So I have 2 inputs that give me the same output. I have a continuous differentiable function. And so then Rolle's theorem says that f prime of x is 0 somewhere, that there's some x value c where the derivative is 0. So somewhere. Well, where could that possibly be? Well, let's just look at what the derivative actually is. If f is x cubed plus 2x minus 1, then f prime is 3x squared plus 2. But wait a second, that never gets any smaller than 2, because 3x squared is greater than or equal to 0, and if I add 2 to that, I get something which is greater than or equal to 2. So in other words, f prime is never 0. So we said if there were 2 roots, f prime had to be 0 somewhere, And if f prime is never 0, well, that means that I can't have two roots. Okay, so that's a very typical application of Rolle's theorem. And so next time we're going to see how to prove the mean value theorem using Rolle's theorem.